Inversion of control shifts responsibility for object management from the developer to the framework. Instead of manually instantiating every class with the new keyword, the Spring framework handles the creation, configuration, and state management of those objects. But if you aren't writing the instantiation code yourself, how do you ensure an object receives its exact dependencies or opens necessary database connections at the right time? The Spring IOC container manages these complexities through a standardized operational sequence. This 7-step pipeline governs a bean's progression from initial discovery to final destruction. Looking at the first 2 steps, the container scans the application for specific classes and creates the raw, unconfigured objects. Next is step 3, dependency injection. This is the precise moment the container wires the application's architecture together, supplying each raw object with the dependencies it needs to function. Steps 4 and 6 define the lifecycle hooks. The init method prepares external resources, and the destroy method cleanly closes them down once the object's job is done. The Spring container operates as a strict mechanical system. Understanding exactly how and when it executes these stages is the only way a developer can maintain architectural control over the application. Before any dependency injection can occur, the container must first figure out which classes it is supposed to manage. This brings us back to step 1 of the pipeline. The framework uses the @component_scan annotation to identify target packages where these valid component classes reside. In standard Spring applications, this requires explicit configuration. The programmer is strictly responsible for providing the exact base package attribute externally. Spring Boot automates this process. Instead of requiring external configuration, Boot designates the package containing the main or starter class as the default base package. From that starting location, the framework automatically scans downward, checking that package and all of its nested subpackages for components. Once those classes are located, the container moves to step 2, instantiating them into empty objects waiting to receive their dependencies. Proper component scanning is a mandatory prerequisite. A misconfigured base package leaves the container blind, preventing the lifecycle from beginning. Moving to step 3, the container must now link these empty objects together. It achieves this loose coupling primarily through the @autowired annotation. By default, @autowired operates with an internal attribute set to required equals true. This dictates that any dependency marked for injection is strictly mandatory. This diagram illustrates the 3 specific outcomes the container faces when attempting to fulfill that mandatory dependency requirement. Case 1 is the ideal scenario. The container searches the context and finds exactly one matching dependency object, labeled here as Class B. Because there is no ambiguity, the container automatically and successfully injects the dependency into the requesting object. Case 2 occurs when the container searches the application context but finds 0 matching dependency objects. Because the required attribute is true by default, the missing dependency causes the container to throw a fatal no such bean definition exception, halting execution. A developer can override this strict behavior by manually setting required equals false inside the @autowired annotation. With this override active, the container suppresses the exception and instead injects a null value.
This allows the application logic to safely handle an optional dependency. Case 3 introduces ambiguity. Here, the container finds multiple viable child objects, B1, B2, and B3, and cannot mathematically determine which one to choose. This tie results in a no unique bean definition exception, as the container expects a single bean, but is confronted with several candidates. To resolve this, developers must intervene, typically by using qualifiers or providing additional configuration metadata to specify exactly which bean should be injected. While @autowired eliminates manual object wiring, it demands absolute clarity in the application's object graph to prevent catastrophic crashes during startup. Once the object graph is wired, the container proceeds to step 4, the init method, and eventually step 6, the destroy method. Unlike Java servlets, which strictly mandate initialization and destruction phases, Spring treats these lifecycle methods as purely optional. If implemented, the init method executes immediately after all dependencies have been successfully injected. It is specifically designed to perform setup operations, like opening database connections or loading configuration data. Conversely, the destroy method executes right before the bean is removed from the container. This provides a final opportunity to release held resources and cleanly sever external connections. Spring provides 3 distinct syntaxes to activate these lifecycle hooks: XML configuration, predefined interfaces, and annotations. The first method relies on XML configuration, using the init method and destroy method attributes directly within the bean definition. The second method utilizes Spring's predefined interfaces, requiring the developer's class to implement initializing bean and disposable bean. However, this approach tightly couples the developer's core business logic directly to Spring-specific framework code, reducing overall modularity. The third method uses JSR 250 annotations, specifically at postconstruct for initialization and at predestroy for cleanup. This is the modern standard. If used within an XML-based setup, it requires the addition of the context annotation config tag and the relevant Java API dependencies. Regardless of the syntax used, there is a critical mechanical rule. The container will not automatically trigger destruction methods unless the developer explicitly calls the close method on the application context. There is also a specific edge case for prototype scoped beans. The container will execute their initialization, but it abandons them afterward, leaving the developer solely responsible for managing their destruction. Choosing a lifecycle configuration method is an architectural decision, balancing ease of implementation with how tightly you want to bind your code to the Spring framework. This complete 7-step pipeline serves as a structural roadmap. It tracks an object's exact journey through the Spring framework. A correctly configured bean gets discovered during scanning, survives the strict cardinality checks of autowired, and reliably passes through its predefined lifecycle gates. Mastering the rules of dependency injection is required to prevent immediate application startup failures and resolve ambiguity errors before they halt execution. Properly implementing init and destroy methods ensures the application maintains stable connections while preventing memory leaks. Inversion of control is a highly predictable, strict mechanical system. It rewards developers who understand the exact moments they need to intervene and precisely how to exert that control.